All right, second video for 11.2. We did limits in 11, or in the first video. Now we're going to talk about continuity, which also has some similarities to what you've seen in 2D. So we've done the limit parts, now we're just going to talk about continuity. Okay, so you've seen something like this before. A function is continuous at a, b, if your limit is xy approaches ab, f of xy equals f of ab. Okay, so the function has to exist, the limit has to exist, and the value of the function has to equal the limit. So it's the same thing as you saw in 2D. Okay, we could say a function is continuous on its domain, which we would represent just D, okay, if it is continuous at every point AB in D. Okay, so an example of that, I'm just taking it really basic, 2D, if we have f of x equals 1 over x, okay, your domain there is all x such that x does not equal 0. Okay, so it is continuous on its domain. Okay, we would say it's not a continuous function, right? Because remember that old trick, I have to lift up my pen to draw it. But it is continuous on its domain. So wherever the function is defined, where the function is defined, it's continuous. Okay. So be careful with that. There's a difference between being continuous at a point and being continuous on a domain and just being a continuous function. Okay. So some other examples here, we might have the limit as xy approaches, say, 1, 2 of x squared y cubed minus x cubed. I don't know why they gave you such a weird one to start out with, but that's okay. Just like in 2D, direct substitution works, right? You can plug in x equals 1, you can plug in y equals 2, you should get 11. Okay, this is a polynomial. So all polynomials are continuous, whether it's in one variable or two variables. So you can direct sub. It'll always work. Okay. Another example, we can have the function okay. Remember, rational functions, just like 1 over x, are continuous everywhere except where the denominator is 0. Okay. So in order for the denominator to be 0, x would have to be 0 and y would have to be 0. Okay, so the domain of this function is all xy pairs, just as long as it's not 0, 0. Anything else, one of them is allowed to be 0, the other one could be 0, just as long as they're not both 0. Okay, and then it's continuous on its domain. Okay.
A phone was found in the cafeteria after second lunch. If you believe it's yours, please stop by the security desk after school today. If you believe you lost your phone in the cafeteria, it is at the security desk. You come after school to claim it.
I don't think any of you lost your phone today. Okay. Another one, if we say, all right, well, let's make it a piecewise function. X squared minus y squared over x squared plus y squared. If xy does not equal 0, 0, And let's say it's 0 if xy equals 0, 0. Okay, well, we just learned that the limit, this was one of the first examples in the previous video, we did this, of x squared minus y squared over x squared plus y squared does not exist. Okay, I think that was the first example in video 1. Okay, so you can't just define it. Like, I put 0 there, we could just as easily put 8. So it doesn't work, okay? Because as we approach x squared minus y squared over x squared plus y squared, that limit doesn't exist, okay? So this one would not be continuous. And not only that, it's not continuous on its domain, because now it is defined for all values, right? Your domain for this one, such that x, y isn't anywhere in two-dimensional space. Okay, it is defined everywhere, but it's not continuous at 0, 0. It's continuous everywhere but there. Okay. Next one. F of xy equals, we have already seen this one before too, right? 3x squared over y, x squared plus y squared. Oops, I gotta make my bracket longer there. Okay. If xy does not equal 0, right? Because that would be undefined if xy is 0. And it's 0 if xy equals 0, 0. Okay, so now it's defined everywhere. Its domain would be all real numbers. So its domain all xy such that they're in real space. Okay, and we did our squeeze theorem on this guy in the previous video. So your limit xy goes to 0, 0 of 3x squared over y over x squared plus y squared is 0. Okay, we proved that again with the squeeze theorem in the previous video. And that is the same as what f of 0, 0 is. Okay, so we have now filled in that hole where this is continuous, not only on its domain, but the fact that its domain is all real numbers in 2D space. It's continuous everywhere. If we had filled this in, now I couldn't have replaced that with 8, okay, because then this part would not be true, okay? F of 0, 0 would have been 8, which wouldn't have matched the limit, so it wouldn't have been continuous. But just like in Calc BC or Calc AB, you filled in that hole there, so it works, okay? I think we can do one more. So this one won't be too long of a video, I guess. H of xy equals arc tan of y over x. Okay, now this is a composite function, okay, where if we have like f of x, oops, I get my two variables in there. F of xy is y over x, and g of xy is the arctan of f of xy. Okay, we've got a composite function going on here. So for composite functions, if f is a continuous function of two variables, and G is a continuous function in one variable, and defined on the range of f, then g of f of xy, which would be h of xy, your composite function, is continuous. Okay, so I have labeled these just like they're labeled in the paragraph there. Okay, so we've got our f is a continuous function in two variables. It is continuous on its domain, right? As long as x does not equal 0, it's continuous on D, where D is all xy such that x does not equal 0. Y can be whatever we want. Okay. Next, we got our G. G is a continuous function in one variable, and it's defined on the range of f. So let's go back in the range of f. Okay. So what kind of outputs can we get? Man, anything we want. Okay. We can get 0 if y were 0. We can get anything else that we want. So your range would be all real numbers. Okay. And that's not in two-dimensional space, right? Because your range, your output's just going to be one value. Okay. So G is a continuous function in one variable. Okay. Your G of x is the arctan of x, basically, right? And we're just putting in f of xy in place of x. Okay. Your arctan graph is continuous everywhere. Okay, remember your arctan graph looks like that between pi over 2 and negative pi over 2. Okay. So your inverse of your tangent graph, right? So that's true. Okay. So then we have, what should make sense, is your h of xy, which is your arctan of y over x, is continuous everywhere except when x is 0, just like f of x. So it's continuous on the domain of f of xy, basically. I guess I should have added that. Okay, it is continuous, so you can be specific about where it's continuous. Okay. All right, that's about it. If you look in your book, they did do more with epsilon delta notation when you have 3 or more variables, which if epsilon delta, or delta epsilon, sorry, if delta epsilon was confusing in 3D space, once you add even more than that, it gets even more confusing. So we are going to stop there, and that's it for 11.2 then.